All right, thank you very much. So first of all, thank you for inviting me to give a talk at your seminar in Nottingham, and thank to everybody for coming. So I'm happy to report about this joint work in progress with Patricio Gallardo, Gregory Pearlstein, and Zheng Zhang. And we will be studying compact moduli of Horikawa surfaces. So I would like to start by clarifying what do I mean by a Horikawa surface. So this will be a smooth projective connected surface. We will be working over the complex numbers. We want our surface to be minimal, which means we don't have -1 curves. And this is a surface of general type that satisfies the following properties. So the square of the canonical class is 1. The geometric genus, which is the dimension of the second cohomology group of the structure sheaf, will be equal to 2. And the irregularity of the surface, which is the dimension of the first cohomology group of the structure sheaf, we want it to vanish, to be 0. So this is a fundamental example in the study of the geography of surfaces of general type. These surfaces lie very close to the Nitras line and were studied by Horikawa back in the 70s. I also would like to mention that actually in the literature, there are other types of Horikawa surfaces for different choices of invariants, k-square, pg, and q. However, today we will be really concerned with this specific type. So I will simply call them Horikawa surfaces, hoping that we will not get confused. Okay, so I will just refer to those. If this definition may feel a little bit abstract, I can assure you that those surfaces have a very explicit realization. So it is a result attributed to Kodara that if we look at the linear system associated to twice the canonical class, this induces a degree 2 morphism onto the weighted projective plane P112. Which you could also think of as being the quadric cone in P3. So a cone over a smooth plane conic. And this map is generically finite, but it may contract some curves. So to fix this, what you could do is to pass through the canonical model of the surface, which we will denote by SC. And this is obtained by contracting a bunch of -2 curves, which will introduce at worst some ADE singularities. And by doing so, you will make the canonical class ample because KSC will be now an ample divisor. And this birational contraction also factors the original degree 2 morphism we had, giving you a 2-to-1 cover of P112. Very natural to ask, where is this covering branched? And I can quickly answer that. This 2-to-1 cover is branched along a curve of degree 10. So given by the vanishing of a polynomial of weighted degree 10 in the variables x, y, and z. So x and y will be my variables of degree 1 and z is of degree 2. So it will appear at most at the power of 5 in our expression for the polynomial. And this is particularly nice because you can write down SC with a single equation. So SC will be given by the vanishing of w squared minus f10, this polynomial, inside weighted projective space P1125. So w is my newly introduced variable of degree 5 that I used to make the double cover. All right, so let me know if there's any questions so far. This is the description of the objects that we want to study. And what we would like to do is study moduli of those surfaces. And so the starting point for moduli of surfaces of general type is the work of Gieseker back in the 70s, which guarantees the existence of a quasi-projective coarse moduli space MH, parametrizing, of course, in our case of interest today, the canonical models SC of our Horikawa surfaces. So maybe to get a feeling of this moduli space MH, we may start by computing its dimension. And you can do this in many ways. Here is a quick way to do it by, first of all, counting. So we realize that the canonical model depends on this curve of degree 10 in P112. And so what you can do is start counting the monomials that you have of degree 10, x to the a, y to the b, and z to the c. Quick enumeration gives you that we have 36 of them. Then we subtract 1 because of projective scaling. And finally, we subtract 7, which is the dimension of the automorphism group of P112. Putting everything together, we get that MH is a 28-dimensional moduli space, which is fairly high dimensional. And at the center of today's discussion will be the problem of compactifying this moduli space, MH. Before discussing the details of the compactification, though, I would like to give you some motivation, like why it's interesting and important to understand compactifications of this specific moduli space. So certainly the high dimensionality makes it a tough problem, but there are also other reasons that I would like to discuss. And the very first point that I would like to make comes from Hodge theory. So it turns out that the period domain for those Horikawa surfaces is not Hermitian symmetric. Without giving the details of the definitions of those technical terms, I'd rather analyze a consequence of this, which is that the classical Bailey-Borel and toroidal compactification methods do not apply to this case. Recall those are some compactification techniques, Hajj theoretic compactification techniques that you can use, for example, in the context of moduli of principally polarized abelian variety or lattice polarized K3 surfaces. And we don't have them available in the non-Hermitian symmetric case. And actually, this was great motivation for work of Kato and Unsui and Green, Griffiths, Laza, and Robles that aim at generalizing those techniques, Bailey-Borel and toroidal, in this non-Hermitian symmetric case. And by the way, this example that we want to discuss today of Horikawa surfaces will be really the very first non-trivial example that you want to study within this framework. At the same time, there are also other compactifications that we have available and attracted attention lately. Starting from the compactification provided by the use of geometric invariant theory, which gives projective compactifications using quotients by algebraic group actions. And a nice compactification, which I will denote by MH bar GIT, was constructed by David Wen in an archive preprint back in 2021. And I will come back to this at a later point of the seminar. A remark that I want to make, though, is that when studying GIT types of compactifications, what happens is that the boundary tends to be quite small, not necessarily divisorial. And for this reason, those compactifications tends to be fairly singular at the boundary. And in particular, in the presence of strictly semi-stable GIT points, the geometric meaning of the points of the boundary could become weak. For these reasons, it is natural to also consider other compactification perspectives. For instance, the one that comes from the work of Kolar, Shepherd-Baron, and Alexeyev, which here I denote by MH bar KSBA. So this is the compactification method that makes use of the minimal model program. And if this is something that you hear for the first time, roughly speaking, the way to think about this is as an analog of the dilemma for Knudsen compactification, MGN bar for curves with marked points, but adapted to moduli of higher dimensional algebraic varieties, such as our Horikawa surfaces of interest. So my plan now, of course, let me know if there is any questions so far. And my plan would be to tell you what are the general features of this compactification. Okay. So let's take a moduli space M, parametrizing your algebraic varieties of interest. And the KSBA compactification has this property of being geometric, which means that the point in the boundary also parametrize algebraic varieties, which should be thought of as degenerations of the varieties that M parametrizes to begin with. And those are called stable varieties, or in the presence of a divisor, more generally stable pairs. Okay, so we have a geometric compactification, which parametrizes those stable varieties or stable pairs in a modular way. We have a coarse moduli space, so it's well behaved with respect to families. And also, strong of our experience that we have with MGN bar, this compactification is expected to have a rich boundary structure, which means divisorial boundary with an interesting combinatorial structure to study, as in the case of MGN bar. Along with this, also, there are some interesting problems and to consider and investigate. Starting from the fact that in complete generality, the structure of the boundary of this compactification, it's unknown a priori. For example, you do not know a priori what are the stable varieties or the stable pairs which the boundary parametrizes. So for this reason, you have to go ahead and study them. And by doing so, in general, could be hard because it involves the minimal model program, often in high dimension. And so those are some interesting, compelling points about studying these compactifications. A second point is it's also interesting to understand this and study how this compactification method is related to other compactification methods that we discussed. For example, the one that come from GIT or the Hodge theoretic ones. So understanding the interplay between these different perspectives will certainly be something of interest in today's discussion. So this is the end of my general introduction about this compactification. Next, I would like to give you the basic ingredients to work with it, and then we will apply them to the case of Horikawa surfaces. So back to the beginning in some sense. So the building block of this compactification method is the notion of a stable pair. So which is the data of a variety X and a divisor D with Q coefficients in between 0 and 1, such that the pair is not too singular. It has to be semi-log canonical. So this is saying, roughly that it shouldn't be too singular. More explicitly, one of the parts of the definition of being semi-log canonical asks for having at worst nodal singularities in codimension 1, which is, for example, what you see with stable curves, right? And then the definition is rather technical, so I will not give you all the details of it. So rather, I will move on the second condition, which asks for the canonical class of X plus the divisor D to be an ample divisor. Okay. So note that this is a Q divisor, so you need to multiply it by an appropriate multiple to get a divisor, and then that has to be ample. And a quick note, here I have been discussing stable pairs in general, but if you're interested in the case where the divisor D is 0, we may call X simply a stable variety. So this is the case where the divisor D is 0. And very roughly speaking, this is the theorem that uses a stable pair to construct compact moduli space, which originated from work of Kolar, Shepard-Baron, and Alexeyev. And of course, throughout the years, there have been many contributions, and I apologize for not being detailed about this right now. This is just to give a rough idea of how it works. So roughly, there exists a projective coarse moduli space, which parametrizes all possible stable pairs, X, D, provided you fix some numerical invariants, okay, so that you get something reasonable. Those numerical invariants, it's something that we're very familiar with, for example, in the context of algebraic curves, when we do MGN bar. So there we fix the genus and the number of points. In the context of Horikawa surfaces, what we would like to fix is the self-intersection of the canonical class, which we know is 1. And we also want to fix the Euler characteristic of the structure sheaf, which is 2, given the numerical invariance that we discussed a few slides ago. But let's apply all this in our situation. So remember SC, the canonical model of a smooth Horikawa surface, S. So SC is a stable surface because, first of all, remember it has at worst 80 singularities. Those are canonical surface singularities, which are semi-log canonical. Like semi-log canonical is a way wider class of singularity types. Also, as C had ample canonical class, and so we also have the second part of the definition. So we can consider MH bar KSBA, which I would like to define as the projective moduli space that parametrizes all the stable surfaces as C and their stable degenerations. So to reiterate, those stable degenerations are not known. That's why we're here. We want to understand them, and by study them, we get the global geography and geometry of the boundary of this compactification. Let me know if you have any questions so far before I make some further remarks.
There are no questions at the moment.
Okay. Very good. Okay. So the first remark that I would like to make is, from the way I stated this theorem, when you summon this compactification, a phenomenon that may happen is that suddenly you see many irreducible components that appear, right? And actually, this is totally what happens in the case of our Horikawa surfaces. So the compact moduli space of stable surfaces with k square equal to 1 and Euler characteristic of the structure sheaf equal to 3 has several irreducible components, as it was shown in work of Franciosi, Pardini, Rana, and Rolenske. What I would like to do is focus on the so-called main irreducible components that parametrizes the, on a dense open subset, the smooth Horikawa surfaces, and also those canonical models. Okay. Of course, the problem of identifying this main component in a modular way, it's a very important problem, but today we will not worry about that. So we just pick the main irreducible component. Also, another remark that I would like to make, maybe some of you is wondering about this. So somehow I bothered to describe the theory starting from the general definition of stable pair with a divisor, right? While then, actually, in my case of interest, I picked the divisor to be 0, right? So you may wonder, why did you do it so in generality at first? So first of all, okay, simply for informative purposes, but actually there are some technical reasons which actually come in the proofs of the main results that when I will get to state them, where handling pairs with a non-zero divisor actually has a very important role. So, so the reason why you also want to be able to handle pairs with a non-zero divisor is technical and somehow embedded in the proof of the main results that we will discuss. Before stating those main results, I would like to quickly survey what is known about this compactification MH bar KSBA, because a lot of work has been done. Starting from the work of Franciosi, Pardini, and Rolenske. So what they do is they identify a partial compactification, which is in some sense intermediate. It's contained between the interior of our moduli space and the KSBA compactification. And we can define it set theoretically as being the set of points of the KSBA compactification that parametrize stable surfaces with Gorenstein singularities. So this is kind of putting, some sort of bound, restrictive bound, but still interesting and still gets you to investigate the boundary structure. And they give a very detailed description of this, more than I can possibly show you in this slide. So here I will just give you a couple of features. So the boundary of this partial compactification is 20-dimensional. So it's fairly high in codimension, and it's not pure in the sense that it has several maximal irreducible components, 20 being the maximal dimension. And also they translate in very concrete terms what it means for a stable surface of parametrized by MH bar KSBA to be Gorenstein, which roughly means it has at worst an isolated elliptic singularity. Yeah. You can go way deeper in this description, but that's all I will say for time reasons. There was also a follow-up work to this, together with Rana. they were able to identify two entire boundary divisors in this compactifications that here I will denote by D1 and D2. And on a dense open subset, those boundary divisor parametrize irreducible stable surfaces with a unique cyclic quotient singularity. And in the case of D1, the generic surface parametrized by it has a 1-4-1-1 isolated singularity. So you should think of this as an isolated singularity introduced by acting with a cyclic group of order 4 in an appropriate way on C2. And D2 generically parametrizes surfaces with a 1-18-1-5 type of singularity. Okay. And in some sense, our results, which I will state in the next slide, are complementary to this work, in the sense that we were able to identify other boundary divisors which are different from the ones that were studied by Franciosi, Pardini, Rana, and Orlensky. So I am ready to state the main results. Make a small pause in case there's anything you want to ask me. Okay. So to be able to state the main results of today's talk, I need to first introduce a tiny bit of terminology. So capital sigma for us will denote one of those 8 symbols, E12, E13, E14, blah, 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 all the way down to W13. If you're not familiar with those symbols, those indicate certain specific type of non-log canonical isolated surface singularities. In the same spirit, you say this is an A1 singularity, an A2. Those are others, not log canonical. And very soon, I will describe them to you by not only giving you equations, I will also show you some pictures of those singularities. But for now, let's just think of those as being what I said, and some certain non-log canonical isolated surface singularities. And so here it comes. So this main theorem is organized in 3 parts. The first part is concerned with studying the KSBA compactification. The second point will be relating this to GIT. And the last point will be relate the KSBA to the Hodge theory. So let's start with the first one, which says that we are able to identify 8 irreducible boundary divisors, D sigma. So one for each one of those singularity types. And those are different from the one previously found by Franciosi, Pardini, Rana, and Orlensky. And on a dense open subset, those divisors parametrize stable surfaces which break into 2 irreducible components. So we start witnessing some breaking behavior of those degenerate Horikawa surfaces. And the 2 pieces of the degenerations will be Y sigma tilde and Z sigma tilde. So you may wonder what is the geometry of those 2 individual pieces. And that's what I would like to show you in the next click. So in the middle, you can see a cartoon of the surface with 2 rectangles that are supposed to represent the 2 irreducible surfaces. And the common edge is supposed to represent the curve along which they are glued. And which is always isomorphic to a P1. The Y sigma tilde surface turns out to be an ADE K3 surface. So it's a surface with ADE singularities. And if you take the minimal resolution, you get a smooth K3 surface. And actually, those Y sigma tilde are hypersurfaces in weighted projective space. And they recover 8 of the 95 families in Miles-Reed list of K3 surfaces in weighted projective space. And by the way, it's not that they recover the full families. So they're full, in each type, they recover the full dimensional family of those K3 surfaces. The story for Z sigma tilde, it's slightly more involved. So we can say that it has finite quotient singularities. The H2 of the structure sheaf is 1. H1 of the structure sheaf is 0. And in 5 out of the 8 cases, we can show that it's birational to a K3 surface in a non-trivial way. If you're really curious about which one of those cases I'm talking about is the Z's and the W's. So what happens with the E's, E types like E12, E13, E14? Well, basically, the technique that we apply in the Z's and the W's just does not work for the E's. And we actually conjecture, this will be object of most likely future work, that it's not birational to a K3, rather to some surface of general type. But we're still trying to understand that part. So this is the end of the statement as far as the KSBA theoretic results are concerned. Next is the relation with geometric invariant theory. So I'm referring to the compactification studied by David Wen in 2021. So what we have is a rational map that goes from KSBA to GIT, which is the identity in the interior of those compactifications. So recall that those compactifications compactify the same moduli space. It turns out that this rational map extends to the interior of those boundary divisors, the sigma. So you can define it on a dense open subset of each one of those. And mapping points in the interior of those boundary divisor to orbits of stable points in the GIT. In other words, equivalently, if you look at this degeneration given by this stable degeneration given by two irreducible components, if you look at it through the glasses of geometric invariant theory, you see something that is stable. And it's very interesting to see geometrically what happens when you go from one moduli space to the other. Basically, the GIT forgets the information encoded in the Y sigma tilde part of the degeneration. So actually what happens is that there is a contraction of those divisors when you go to GIT, and the relative dimension of this contraction is given exactly by the number of parameters that Y sigma tilde depends on. So this is the GIT theoretic picture. Lastly, to complete the interplay between the different methods, I would like to mention what happens from the point of view of Hajj theory. But this, I would like to give it a little bit of an introduction of its own before stating it, because it may sound fairly technical at first, what I'm about to say. So one of the building blocks of Hodge theory is that if you have, say, a smooth projective variety, you have something that is called a pure Hodge structure. And that is basically induced by the Hodge decomposition that you have on the middle cohomology group of your variety. Now, if your variety starts degenerating, it acquires an isolated singularity, or maybe it breaks into several irreducible components, you may not have any more a pure Hodge structure, but you always have something called limiting mixed Hodge structure. And there are some cases, though, in which the limiting mixed Hodge structure is actually pure. And an important example of this is, for example, stable curves of compact type. Those are the curves whose dual graph is a tree. Roughly speaking, our Hodge theoretic results is that those stable degenerations that we find are the analog, in the case of Horikawa surfaces, of the curves of compact type, because the limiting mixed Hodge structure of those degenerate surfaces happens to be pure. So this is the end of the statement of the main results. And I make a little pause in case you want to ask me anything. I drink a sip of water. Okay, check the time. Perfect, so I roughly have 20 minutes left. So what's my plan? After stating this theorem, I would like to discuss how those boundary divisors are constructed, because now it's just like an existence statement. So how do they look like? How do you construct them? And by doing so, we will also get a glimpse into the proof of those results and what techniques we use and how we combine them. Okay. So construction of the divisors. So our philosophy, in some sense, it's very much similar to what Franciosi, Pardini, Rana, and Mrolenske do. the question that they ask is the following at the beginning of their work. So somehow, what are the simplest log canonical singularities that a Horikawa surface can acquire? And so they look at the Gorenstein, then they look at the cyclic quotient singularities, and they give you a complete classification. We ask a very similar question, but it's a little bit transverse to that. Transverse because what we ask is, what are the simplest, not log canonical, isolated singularities that a Horikawa surface can acquire as it degenerates? And the answer, you get to the answer by thinking in the following way. You should be considering isolated surface singularities of modality 1, which are not log canonical, and that can be realized, say, at the point 1, 0, 0, 0 of a surface S0, which is given by the vanishing of W squared minus F10. So the very same shape that a Horikawa surface has, or rather the canonical model of a Horikawa surface has. I'm talking about this modality, which is an invariant that you attach to isolated singularities. It is somehow an invariant that counts roughly on how many parameters. It depends. For example, 80 singularities have modality 0, and those are canonical. When you move to modality 1, you see, for example, elliptic singularities, which are log canonical, and those have already been considered by previous works, as we explained. But if you look more in detail, there is a complete classification of surface singularities of modality 1, which was done by Arnold. And you see the list, and you just go look for the ones that satisfy our selecting criterion over here. And you find that there are 13 of them, just taken right out of Arnold's paper. Those E's, those Z's, and those W's. And what I am giving you here, I am giving you the equation of the germ of the singularity. So I am living in a fine three-dimensional space, A3, with coordinates Y, Z, and W, and you should be looking in a neighborhood of the origin of this affine space. So here are the equations. And one thing that I would like to propose, especially since I am giving a slide talk, it would be quite missing out if I didn't show you some pictures. So here are some pictures that you can obtain with the software Surfer of those isolated singularities. So I don't really have an important reasons to show you this, except for the fact that they look nice. And my favorite one is the one in the middle with the 3 branches coming out. And so these are the isolated singularities that we will deal with. But now maybe I actually confused some of you, because we've been talking a lot about how this KSBA compactification parametrizes surfaces with log canonical or semi-log canonical singularities. So why are you looking at those not log canonical ones? Certainly those are not parametrized by your moduli space. So what is going on? Completely fair point. This is just the beginning of a procedure that we need to initiate. And I will now illustrate. So for each sigma, to construct the divisor d sigma, you have to run the following program. First, you need to produce the general one parameter smoothing of this singularity. So remember, S0 is the surface which has this isolated surface singularity. And you need to fit it as the central fiber of a one parameter family over delta, which will be the spectrum of the ring of formal power series. This will be my model for an infinitesimal curve. And yes, so you first do this. You smooth it in a one parameter family. After you run what is called the stable replacement, where of the central fiber of this one parameter smoothing. So I denote the stable replacement by priming everything, the base of the space. I will prime the family, and I will prime also the central fiber. Where now this S0 prime will be a stable surface and will be parametrized by a point of the KSBA compactification. But of course, what is the stable replacement that I'm talking about? Let me illustrate this procedure with a picture. So in the picture that you see right now, let's focus on the bottom left. The picture in the bottom left is supposed to represent the one parameter smoothing curvy S mapping to delta. So delta is this line at the bottom, the family it's on top, and those rectangles are supposed to represent the fibers of this family, where the central fiber S0 that sits right here has the additional dot representing the singularity of type sigma. So the fundamental tool that you have in KSBA theory, and here is where the minimal model program comes into play, is that you're guaranteed that after a certain amount of birational modification of the central fibers, which are blow-ups, some contractions, and possibly some flips, and after some combining this possibly with some base changes, so you see here we go from delta to delta prime, you obtain a new family S prime, where the new central fiber S0 prime now may be broken into many pieces. You know, those are supposed to be many irreducible components, but it's going to be a stable pair. So it's going to be a surface parametrized by your KSBA compactification. And this leads us to the definition of the divisor D sigma. The way we define it is as the Zariski closure of the subset of points of MH bar KSBA, parametrizing all the possible S0 prime that we produce this way. So you change the one parameter smoothing, you compute the stable replacement, you collect all the S0 primes, and you get yourself your locus D sigma, closed subset. Of course, there is no guarantee whatsoever that this has to be a divisor, right? This is just a closed subset. It's a stratum of the boundary. So the last step of this program is counting parameters and show that actually this sigma is 27 dimensional. So you obtain that divisor. So a maximal piece of the boundary. Okay, so this is the rough outline of what we do. So maybe as a next step, it would be appropriate to discuss a little bit better how you get started with those smoothings, because that is somehow everything is built upon those, right? And actually, this touches a very delicate issue, which I will express in the following remark. So if you just take any smoothing of one of those singularities, then in general, it could be quite hard to find the stable replacement. I mean, reason for it, it's because the procedure of birational modifications, base changes, and all that could get quite involved. So our strategy is the following. Rather, we focus on some very specific one parameter smoothings of those singularities, for which we can describe the stable replacement procedure in a very simple way. You should do only a single weighted blow-up at the singularity and no base changes at all. So kind of like everything is set up already for you. You just make this blow-up and you're good to go. Of course, there is a big risk involved with this. The intuition is that if you restrict so much your focus on the one parameter smoothings, maybe you will not be able to describe as much as a divisor in the moduli space because you just see fewer degenerations, right? I hope that it may feel like as intuitive because you just consider fewer smoothings. But here is precisely where we get lucky. So although we will consider some specific families, we count our parameters and we get 27. So that's where, you know, we celebrated. We found enough to describe a divisor. Okay, so this is, so what I would like to do next is explicitly describe those smoothings. So we're getting into the most detail-oriented part of the talk, if you'd like. So I will start actually handling equations, monomials, and doing some calculations. So please, if you get lost, let me know. And let me know if there is any questions so far, because before we venture in the last part of the seminar. Which I have 10 minutes, so I think I have enough time to discuss this. Okay, so now, yes, the next slide will illustrate this construction. The first step of this construction is to choose an appropriate weight function for each one of the singularity types, for all the 8 singularity types. And this is a weight function defined on the monomials, x to the a, y to the b, z to the c. And instead of giving you explicitly what those weight functions are, which could be quite not enlightening, let me tell you what are the properties that we want from it. So we want that if you take a general polynomial h of degree 10, and if you break it into its negative weight part, h minus, zero weight part, h0, and positive weight part, h plus, then the surface S0, expressed as the vanishing of w squared minus the sum of the h0 part and the h plus part, it's going to be a surface with precisely one singular point at 1, 0, 0, 0, and this singularity is of type sigma. So this is a way of constructing your starting central fiber of the smoothing, right? That's what we want. Let me give you an example though, because this just feels like just a vague outline. Let's pick as our guide example the E12 singularity type. So sigma is equal to E12. Recall the germ of the singularity is w squared equal to z cubed plus y to the 7th. And we define our weight function to be the following. So you completely ignore A, and you take 6 times B plus 14 times C minus 42. So there are many reasons why the weight functions looks like this. Of course, it makes what I declared above happen, and that's enough motivation to have it. But maybe one thing that we can quickly appreciate just by looking at it is that those two monomials here, x to the 4th, z cubed, x cubed, y to the 7th, if you apply this formula, you'll realize that have weight 0. And actually, if you go across all the 36 monomials of degree 10, those will be the only monomials of weight 0. So we can see that this weight function somehow in the weight 0 part is responsible for the germ. So the 0 part, h0, is the germ, and the h plus is responsible for making sure that that's the only singularity that you have by adding some higher order terms. But then you may wonder, well, what do you do with h minus then? Is that helpful at all? That is actually very helpful because the h minus part is what gives us the smoothing into the one parameter family in the following way. So if you have a monomial of negative weight, we define the following t star action. So t star, a monomial x to the a, y to the b, z to the c, will be t to the following positive number, which is negative the weight of the monomial, multiplied by the monomial. And then you can define t star h minus extending by linearity on each monomial. And this is going to give you the smoothing parameter. So we define our family S, one parameter family, to be the vanishing of w squared minus the sum of t star h minus, h0, and h plus. And by the way, this will be the correct deformation parameter so that you can compute the stable replacement almost effortlessly. So somehow everything is put there. Of course, you could simply add plus t, but then it may become more complicated to do the stable replacement. That's the philosophy. One quick reason, one quick note that I like to point out, you may notice that this weight function in the degree 12 case is divisible by 2. So that actually is not random, and it's again related to just having the correct smoothing, and that 2 factor is related to the double covering property that those surfaces have. So it's all picked accurately, so that everything works out as we declared. Now you should just take a single weighted blowup of S at the point 1, 0, 0, obtaining S prime. Y sigma tilde will be the exceptional divisor of this weighted blowup. Remember, we're blowing up a threefold, so we obtain an exceptional surface. And And Z sigma tilde will simply be the strict transform of the original central fiber S0. Let me show you this in, again, this running example of E12. So let's first focus on the left-hand side of this diagram, where we have, by construction, S lives in P1125 cross delta as this hypersurface. Then we take a blow up of this fourfold, P1125 cross delta, at the following ideal. So what I gave you here is the ideal sheaf that you should blow up, which is supported precisely where we want the blow up to happen. This will produce a new fourfold, X prime, that has as exceptional divisor the weighted projective space P161421. If you look at what happened at the level of S, this induced a blow up of curvy S as well. We obtained S prime, and the exceptional divisor of the blow up S prime to S is denoted by YE12 tilde and sits inside this other exceptional divisor as a hypersurface. And it will be actually a hypersurface of weighted degree 42. And if you notice, this exceptional weighted projective space is technically called well-formed. YE12 tilde will be a quasi-smooth hypersurface. And if you're familiar with a junction formula in weighted projective space, you quickly realize that this has to be a K3 surface. The reason is that the sum of those weights, 1, 6, 14, and 21, adds up to the degree of the surface, which is 42. So that's how you get those K3 surfaces. So this is all nice. This is all like calculations that you can do, constructions that you can make, but you need to remember that unfortunately there is no guarantee that what we just produced is a stable pair. You actually have to go ahead and prove it, right? We just made this procedure. So the very first big result that we prove, and this is quite lengthy, especially because there are 8 cases to carry, to work with. Actually, it took some time to try to write down some sort of discussion that is organic as much as possible across the 8 singularity types, because each one has its own perks, its own characteristics. And so the very first main result, you need to make sure that this reducible surface we just produced is stable. And this is, I think, the last thing that I wanted to mention now is I'm going almost to 50 minutes, so I can probably stop here and leave time to questions. So thank you so much for your attention.